Yeah, so hello, everyone. I start with 1 minute delay. Now, the tutorial was canceled today. I had trouble with my computer. I will record the tutorial and post recording on eClass later on today, but probably in the evening because I have to attend a couple of meetings today. Of course, I'm going to post the recording of this lecture as well. So last time, as you remember, I hope you can still hear me. Can you?
Yes, we can hear you.
Yeah, you can. Good. Thank you very much. Last time we calculated the electric force exerted by that thin line of charge acting on charge Q0. So the line of charge was positive, Q0 was also positive. And we calculated that if this line of charge is infinitely long, then the force acting on that charge Q0 is given by this expression, which is written here. The force in terms of direction is radially away from that line of charge. So this angle here is 90 degrees. This is the radial direction. And the magnitude of the force is equal to 1/2 pi epsilon naught Q0 lambda divided by y, where y is the perpendicular distance from Q0 to that line of charge, and lambda is the linear charge density. So that was the result. And then we use this result to calculate the force due to plane of charge. So this is the plane of charge, which is in XZ plane. That charge we took to be positive, and charge is uniformly distributed on that plane of charge. I repeat again, the plane is in XZ plane. And then we wanted to find the force acting on charge Q0, which I also took as positive. And the charge Q0 is distance h from this plane, because Q0 is on the y-axis, so h is the perpendicular distance from that plane. And calculations are not trivial, and it will require quite a lot of your time to really understand the solution. So what we did to avoid multivariable calculations, and I know that in your calculus 2015 you will get to these integration over a few variables later on the course. So we will be initially using only integration over a single variable. And to find the force due to the plane on the charge Q0, using just single variable, we divide that plane into many lines of charge. Two of them are shown, one here and one here, but the plane would have to be divided into infinitely large number of these line of planes. So each line of plane would be very thin, let's say thickness dz, and each of these lines, because plane is infinitely large, each of these lines would be infinitely long. And let's say this line of charge produces the force acting on Q0 of this magnitude, which we just derived previously, that F is equal, that constant Q0 lambda divided by capital R, where capital R is the perpendicular distance. This is 90 degrees. This is the radial direction. And that single line of charge repels Q0 with this force, which is called here dF1, in this direction and radial direction. And the force is given by this expression. Now, because to calculate the force due to the plane of charge, we are given value of Q0, we are given h, that perpendicular distance from the charge to the plane, and sigma, which is surface charge density. Now, because lambda is the linear charge density, what we did in previous lecture, we found a relationship between sigma, surface charge density, and linear charge density on each line of charge. And so that was that sigma is dq over dA, where dq is tiny area of rectangular area with sizes dz, dx. So this area dA would be dx, dz, and sigma is amount of charge on that little rectangular area dq divided by that area, which is dx, dz, and dq over dx is lambda, linear charge density. So sigma can be written as lambda divided by dz, or lambda can be written as sigma dz. I substitute for lambda here, sigma dz. This is that substitution. And instead of f, I have written df, because if dz approaches 0, then the force due to that one line of charge, tiny part of entire plane, would exert tiny force on Q0. So that force due to one line of charge will be very tiny compared to the force exerted by entire plane of charge. So that force I designated df. That's contribution for that force Q0 due to one line of charge, and we define the plane of charge into infinite number of lines of planes. So that's why I designated this df. And then we concluded also that for any line of charge in that upper part of the plane, I can find line of charge in the lower part of the plane, such that the z components of these two forces, so df1 is the force due to this line of charge, df2 is due to this symmetrically located line of charge, and as you see, these components of these forces df1, df2 along y direction will add, but components along z direction, these two components will cancel each other. So the resultant force will be along y direction. So we have to find only that y component of these two forces, and the y component of the df1 would be now that df, which we derive df times cosine alpha, where angle alpha is this angle here. This angle I designate by angle alpha from Q0 towards that line of charge Z. And then, so that was done last time. This is just a review still. And then what I did not have time in the previous lecture, to find the force due to entire plane of charge. So here is that calculation. So this is that expression, which is the differential force, y component of that force exerted by one line of charge, right? This is the F1, and component of this is this one along y direction. This is the component of the F1 given by this expression. So now you should observe that in this expression, three quantities are variables, because when I take different line of charge, let's say at different location, maybe this one, then Z would be different. Z is this much. Z is the distance from the origin to the line of plane. So Z would be different. Alpha, this would be new angle alpha, would be different. And R, which is the distance from that perpendicular distance here, that R, this would be R, would be different as well. So there are three variables, Z, R, and alpha. And we have to find a way to express all these variables in terms of just one variable. And that can be accomplished by considering this triangle. This is the right angle triangle in which this distance is Z from the origin to that line of plane. H is constant and given. This is capital R, and this is alpha. So look, cosine alpha is opposite, is adjacent, I should say, sorry, adjacent H divided by hypotenuse capital R. So cosine alpha is H divided by R, or capital R is H divided by cosine alpha, because I would like to express all variables in terms of alpha, which will be the most convenient way to integrate. So I express here R in terms of alpha using this expression. Then Z, which is opposite to alpha, Z divided by H, which is adjacent to alpha, is tangent function, which means that Z would be H tangent alpha. But I need in the expression dz. So I find the derivative dz d alpha. H is constant. Derivative of tangent alpha with respect to alpha is 1 over cosine squared alpha. And then treating again dz d alpha as two differentials, dz can be written as H d alpha divided by cosine squared alpha. So now I substitute this for dz, R, I substitute this for R, and I here made this substitution. Instead of dz, I substituted this. Instead of capital R, I substituted this. And now, as you see, there are many cosine alpha. So cosine alpha, this cosine alpha, and this cosine alpha will all cancel, and h will cancel as well. So the final expression for the differential force y component of the differential force is just that constant 1 over 2 pi epsilon 0 q0 sigma d alpha. Q0 is constant given, sigma is constant given, epsilon naught is constant. So there is only one variable. So I have to now integrate over the entire angle alpha. And this is that. So I integrate both sides of the equation, and the total force Fy would be integral, this integral. But I decided for some reason to integrate first on the half of the half plane, that upper half. So the angle alpha would change from 0, because if the line of charge would be this one along x direction, alpha would be 0. And if the line of charge goes to infinity at z at infinity, angle alpha would approach 90 degrees or pi over 2 radians. Now, because I integrate over half of the plane only, for the entire plane, I have to multiply by 2, because the lower part of the plane will give me the same magnitude of the force. Or of course, somebody could integrate from negative pi over 2 to pi over 2, and then of course the factor of 2 would not be here, right? But the final result would be the same. So again, I integrated only of half of the plane, and I multiply by 2. And integral of the alpha is alpha. I substitute the upper limit pi over 2 minus 0. So the final result is that this 2 and this 2 will cancel, and the total force F is then perpendicular to the plane, right, along y direction, of magnitude q0 sigma divided by 2 epsilon naught. That's the final result. And as you see, so the force acting on the q0 is independent of the distance h of the charge from the plane of charge. There is no h in this expression, which means that whether I put q0 relatively close to that plane or far away from the plane, the force is the same. But remember, this is only true if the plane is infinitely large. And of course, in practice, nothing is infinitely large. But if the plane is relatively large, let's say if this is the plane perpendicular to the screen, and the charge would be relatively close to it, let's say if this is q0, relatively close distance, then the plane perpendicular to the screen here, we could treat as infinity large, because this distance of the charge to the plane would be much smaller than the size of the plane. So that approximation usually we will do and use this result in the future. On many occasions in future lectures, I will be using this result, that the force acting on q0 is independent of the distance from the plane of charge, So this is the important result. As I've mentioned, we will be using it a few times in the future. So any questions right now? You can unmute yourself and ask questions.
Sir, E-class, I think, is down for some people. It took me I had some difficulty signing on to E-class. Could you post this slides in the chat so we can follow through?
Not really. I think that all students registered in the course will have access to E-class. If it is down, then it should be down to all students. So I am not sure about that chat thing. So I will be thinking about your request, but I hope that E-class will, if it is down for some students, it will be problem will be resolved quickly, and I will be posting everything only on E-class. So that's probably what I'm going to do. But they resolve the problems with E-class usually very effectively and very quickly. So this is what I wanted to do regarding calculation of the force due to continuous charge distribution. My kind of now in the tutorials, which I will record today and post recording on E-class, I will solve few additional problems for different charge distributions. And the lesson for you is that we can calculate the force acting on charge Q0, any charge due to any continuous charge distribution, if distribution is not too complicated, like on the line or plane of charge, or maybe the ring or hovering, then the calculations are quite easy. But if distribution is more complicated, then you have to use multivariable calculus, and integrals can be quite complicated. We will not go into these complicated cases because you are in the process of learning that multivariable calculus.
Sir, I have a question.
Yes, please.
Hi. So on the last part where you multiply by 2,
Yes.
why do we do that?
Yeah, I did it because you see, I took integral limits of integration from 0 to pi over 2, which means that I integrated only above this half of the entire plane. Because if the line of charge I take along the x-axis, then alpha would be 0, right? Because now if the line of charge is here, that alpha would be 0. So I integrated from 0 to pi over 2, and upper limit is pi over 2, because when that line of charge goes to infinity along z direction, then this angle alpha will be increasing, will be bigger and bigger. If it go to infinity, that angle alpha will approach pi over 2. So limits of integration I took from 0 to pi over 2. So I integrated over the half of the plane. Now, but the bottom half of the plane would give me the same result, so I multiply by 2. But if you would not multiply by 2, then you would have to take limits of integration from negative pi over 2 to pi over 2. Because you see, when that line of charge would be somewhere here, then the angle alpha, this angle alpha, you would have to take as negative. So that would be, if this angle alpha would approach 90, negative pi over 2, if that line of charge would go to negative z infinity. Okay, so that's the reason why I multiply by 2, because I integrated over half of the plane. Any additional questions? Yeah, so more examples are in the tutorial notes, and my Zoom recording of the tutorial will be posted later on today. So at this point, I would like to share new lecture slides, and I would like to start to teach about electric field, because that force exerted by the charge between two charges, like for example here we have one larger charge which I designate capital Q and smaller charge Q0. These charges now attract, or here in this case repel each other even through vacuum. So that electric force we call now the force which is action at a distance. So there is no connection between charges. They repel or attract one another even through vacuum. So that was a problem for many scientists to understand. So Michael Faraday, long time ago, being puzzled by that interaction between charges through vacuum, he introduced the concept of electric field. So as you remember from physics 1801, because we spent a lot of time in physics 1801 on electric field. So Michael Faraday said that every charge produces electric field everywhere. So let's say this capital Q produces electric field everywhere, and then that force acting on Q0 is sort of mediated by that electric field produced by that capital Q. And so that electric field was introduced just as a way to explain that interaction between charges through vacuum and at a distance through vacuum. Now, today we know from quantum physics that this electric field is quantized, and that interaction between two charges, that mediation of that force occurs due to exchange of photons, which are that particle of light, which is called photon. So photons are exchanged between these two charges, and that's the connection between these two charges, which causes that attraction or repulsion. Now, these photons will never get into your eye, you will not see it because these are virtual photons which live only for very short time. So that principle of uncertainty is not violated. So this exchange of photons mediates that interaction, and that photon is the quantum of electric field. Now, what I'm saying right now is complicated. Many of you are puzzled what I'm saying, but that's how modern physics explains that interaction, that these photons are exchanged. But Michael Faraday, long time ago, did not have any clue about photons. He just introduced that concept of electric field classically. He said, there is something which we don't know what it is. Every charge produces electric field around, and interaction is then mediated by the electric field. And Michael Faraday introduced that concept of electric field, which we designate by capital letter E, as just the magnitude of the force divided by Q0. So look, if this capital Q produces electric field everywhere around, if I put charge Q0 at certain point P, then there will be force acting on Q0. Let's say the force would be acting in this direction, that force F. And if we divide that force F by Q0, that's the definition of electric field, which means that, as you will see, that electric field is really independent of Q0, because the electric field is just the force acting now per unit charge, but that Q0 by definition is positive charge. So electric field has the same direction as the force exerted on Q0, which in this case would be now away from that capital Q in this direction. So the electric field has the same direction as F, because by definition Q0 is a positive charge. Of course, if Q0 would be negative, the force would be in opposite direction, right? So scientists has to decide for the definition whether you take positive or negative charge. So definition is to define electric field, that electric field is the force divided by positive Q0. And that Q0 we call a test charge. We call it a test charge because that charge Q0 is used just to test the existence of the field. So if you want to verify if at this point electric field is present, you would put charge Q0 here. And if there is a force acting on it, that means there is an electric field present at that point. And the magnitude of the electric field you will get by dividing F divided by Q0. So electric field is strong, E is large if F is large. F is large. So that's the definition of electric field, that this is the force exerted by Q0. And the unit of electric field is what? Unit of force is Newton, unit of charge Q0 is Coulomb. So unit of electric field is Newton per Coulomb. Now, in many situations, electric field will be given of, we will calculate first electric field, and then we will try to calculate the force acting on the charge. So you see from this definition, F is equal E or Q times E0. So we will be using this expression very often. If electric field is given, then you can find force by multiplying the charge by the electric field, and that will give you the force acting on the charge Q. So if you multiply charge Q by the electric field at that location of Q, then that will give you the force acting on the charge. So I'm explaining this relatively fast because we spent a lot of time on electric field in physics 1801. So this is just a review. And you see, if we use that definition, for that case, when we have certain charge Q, let's say this is capital Q, and if I want to find the electric field, let's say at this point, here I would put charge Q0, positive charge Q0, and then I would have to find what is the force acting on that Q0 at this point. The force would be radially away. That would be the force acting on that charge Q0. And then by definition, electric field at that point, at this point, where I put that charge Q0 would be F divided by Q0. F by Coulomb's law is K, capital Q times Q0 divided by R squared. This is the distance between these two charges, that is R, and divided by Q0. So as you see, Q0 cancels. And then electric field is equal K, capital Q, which is the source of that electric field, divided by R squared. So this would be electric field at that point where I put the charge Q0. So as you see, electric field is independent of Q0. That will be always the case. Q0 is only just needed for the definition, but electric field is independent of Q0. It will always cancel because electric field is the force divided by that Q0, right? The force acting on that unit charge Q0. Because if Q0 is equal to 1, then E, electric field, is equal to F. Because if Q is 1, then F divided by 1 is F. So then in magnitude, of course, units of E and F are different, but in magnitude, if Q0 is 1, E is equal to F. So we say that electric field is the force acting per unit charge, right? And that Q0 will always cancel. So this is the expression which we'll be using very often, which allows you to find electric field at any point, let's say at this point or any point, which is a distance R from that charge capital Q. This is the expression to find electric field at any point, distance R from that charge capital Q. And this expression is only valid, yes, to find electric field due to a point charge. So that capital Q is a point charge or spherical charge. A spherical charge. Because Coulomb's law, which is this expression, is only valid if Q and Q0 are point charges or spherical charges. So as you see, that electric field depends on square of the distance, 1 over R squared. So you see electric field decreases very quickly. Yeah, just a minute, I will allow you to ask question. You see very quickly with the distance. So at this point, electric field is small, vector is short. At this point, electric field is stronger, that vector E is larger. At this point, electric field would be even stronger, but electric field is always radially away from that positive charge, from the positive charge. So now your questions. You can unmute yourself. Yeah, somebody wanted to ask a question. Well, if you don't have questions, then yeah. So this is that map of electric field.
Sorry, hi, I have a question.
Okay.
You know that K is 1 over 4 pi epsilon 0, right?
Yes.
Isn't the 4 pi times R squared? Because of that, it's a sphere, because like a phenomena is divided into the sphere that at radius R, a sphere of radius R. Isn't it the reason why the formula contains 1 over 4 pi R squared? Because
well, no, that K is just a constant, and it has nothing to do whether it's sphere or not. It's a constant. It's a physics constant. That K we call Coulomb constant, epsilon 0 we call permittivity of free space. It's a constant. But the dependence of electric field as 1 over R squared results from the Coulomb's law, you see, because Coulomb's law, which is the force between two charges Q and Q0, depends as 1 over R squared. So that's the reason why electric field is inversely proportional to R squared. And that's a significant result, of course, right? That's a very significant thing, that this electric force depends on 1 over R squared. So that's the result of this. So now, any additional questions?
There's another law, I think it's Gauss's law, that if we do that, it will result in like a charge divided by the surface area. And
yeah, we will get to Gauss' law pretty soon in maybe a couple of lectures. So I don't want to diverse that right now to Gauss' law, but we will talk in details about the Gauss law.
And I also
yes
have another question. When you said that like electrons or charges like transmit virtual photons to like, and that carries the electric field. Is that the reason why when the intensity or the amount of charge, or basically the intensity of the electric field, which is like proportional to the intensity of the photons they send, changes, basically creates electromagnetic radiation?
Yeah,
So like basically a different photon changes intensity or the number of it, but then creates another photon, something like that.
Yeah, it's a little complicated questions. But if I understand your question correctly, is this: when electric field is strong, an electric field is strong if that charge capital Q is large. If that charge Q would be large in magnitude, not in a physical size, but in magnitude, if Q is large, then it will produce strong electric field. And then the force acting on Q0, if we put somewhere Q0, then electric field at that point will be strong and more photons will be exchanged. So the number of photons, number of photons of this, which I exchange, will increase, right? So that intensity, which is of that electric field, which is proportional to that number of these photons which are exchanged. These are quantum concepts, and I don't want to go or divert myself too much into that quantum concept, because we define that electric field here classically, that there is something around which we call every charge, which we call electric field, and that electric field mediates the force between charges. So that would be maybe at this stage appropriate understanding of that concept of electric field, that every charge produces electric field everywhere around the charge, and the mediation is between charges of that force is sort of mediated by this electric field. But what electric field is, that's a very important question, how modern physics interprets that electric field. So I did explain this a little bit about, but I don't want to go right now too much into that quantum concepts. What I really wanted to say is that instead of drawing these vectors, you see, because electric field is a vector quantity, at every point in space around that charge capital Q, every point in space will have certain electric field, which is indicated by these vectors. These vectors will become, in smaller and smaller in magnitude. But instead of drawing that map of these vectors, very often we just draw these electric field lines like this, which shows the direction of electric field. And for the point of spherical charges, electric field lines are radially away from positive charge. If the charge is negative, as you know from physics 1801, then, if the charge is negative, let's say minus, then the electric field lines are radially towards that negative charge. Direction is towards the negative charge, right? Because if this charge would be not positive, but let's say if this charge would be negative, if we put positive test charge, and test charge by definition is positive test charge would be attracted by negative charge, right? So the electric field due to negative charges are towards the negative charge. So that was all explained in physics 1801. I just wanted very briefly to introduce or to review these concepts again. But my true purpose is to now calculate electric field due to line of charge. And so here you have this line of charge. And remember, in previous lectures, we calculated the force exerted by line of charge acting on certain charge Q0. If I put at point P here charge Q0, let's say positive charge Q0, then the force acting on that charge Q0 due to that line of charge was given by this expression, 1/2 pi epsilon naught Q0 lambda divided by R, where R was that perpendicular distance.
Questions.
Could you, if you have questions, please unmute yourself and ask questions. Otherwise, remain muted. So any questions? Yeah, please remain muted. So this was the expression which I did review today a little bit as well. So this is that perpendicular distance. This is 90 degrees. This is the radial direction, distance R. This was the expression for the force exerted by entire line of charge on charge Q0. So if I use now the definition of electric field, which is F divided by Q0, then I can use the definition to find electric field at point P, which is a distance R from that line of charge, that perpendicular distance R from line of charge. So by definition, electric field produced by line of charge at point P would be the force acting on charge Q0 located at point P divided by Q0. But as you see, the force also depends on Q0, so that Q0 and Q0 will cancel. It will always cancel for electric field, and an electric field due to the line of charge, entire infinitely long line of charge, a distance r from that line of charge is given by this expression, 1/2 pi epsilon 0 lambda divided by r, where lambda is the linear charge density on that line of charge, and r is the perpendicular distance. This angle is 90 degrees. See, point P is distance r, radial distance r from the line of charge. So here I use definition and our previous result, which we derived in previous lectures, to now calculate electric field due to line of charge. So here you have visualization in 3 dimensions, that if this is the line of charge, let's say of very thin kind of wire on which there is a positive charge, then at any point around that wire, electric field goes radially away from the line of charge. But the angle between line of charge and these electric fields is always 90 degrees. You see, these green vectors are perpendicular to the line of, to that line of charge, to that wire of charge. And the magnitude of electric field, as you see, depends on r, not r squared, but on distance, just 1/r. That's the dependence. The larger the distance from the wire, the smaller the electric field. Closer to the wire, electric field is strong. Far away from the wire, electric field would be smaller. But that is the expression to calculate electric field due to line of charge. So any questions, please unmute yourself and go ahead with your questions. Well, if you don't have any...
Is this expression only for like an infinitely long charge, or sorry, an infinitely long line of charge?
That's very correct. This
Okay.
expression here is only and only correct for infinitely long line of charge. But as I mentioned already previously, nothing is infinitely long. So in practice, now like in engineering practice, if the wire would be quite long and the point at which you calculate the field is relatively short distance from the wire, if this is distance r, and the wire is much, much longer than the distance from the wire, then we can make this approximation. And we will be using this expression, exactly this expression, to calculate electric field from the wire at certain distance from the wire. So we will make assumption that wire is very long or infinitely long. Any additional questions?
So could you use this approximation, for example, for power cables, transmission cables?
Yes, that's what we will use that approximation as well for these situations. So usually now the wires will be much, much longer than the distance from the wire. Then you can make that approximation.
Thank you.
Yeah, you're welcome. So on another slide, on the next slide, I have, we will calculate now electric field due to plane of charge. So here we have plane of charge. Let's say the plane is positively charged. Let's say this plane is very, very large, maybe infinitely large. And as you remember, just a few minutes ago, we calculated the expression that if this is the plane, if I put any, say, point charge Q0, positive charge Q0, now certain distance from that plane, then the force acting on that charge Q0 is given by this expression. We just a few minutes ago, we just derived that expression, Q0 sigma divided by 2 epsilon 0. And remember, I was emphasizing that that force does not depend on the distance from that infinitely large plane of charge. So this is the force acting on Q0, the force exerted by that infinitely large plane of charge. So if I now use the definition of electric field as force divided by Q0, then if I substitute for F this expression and divide by Q0, Q0 will cancel again. And then electric field produced by that infinitely large plane of charge is then given by this expression, sigma divided by 2 epsilon naught, where sigma is the surface charge density. And because the force does not depend, the force acting on Q0 does not depend on the distance from the plane, electric field does not depend on the distance from the plane of charge, which is a shockingly counterintuitive result, because many of you would like to now think that when you have a now plane of charge, electric field close to that plane of charge should be stronger, and electric field away from that plane of charge should be weaker. And your intuition is correct, because if the plane of charge is not infinitely large, then electric field at this then electric field depends on the distance actually from the plane of charge. But if the plane is infinitely large, then we got the strange result that electric force and consequently electric field is independent on the distance from that plane of charge. But the plane has to be infinitely large. So again, in practice, we will be using plane of charge, which will be not infinitely large, but large. And then if the point is relatively short distance from that plane of charge, we will use this approximation that electric field is given by this expression. So we will be using this approximation. Of course, in practice, when the plane of charge is finite, then the electric field depends on the distance, but the expression is very complicated. So we will be using this approximation that the plane is very, very large, much, much larger in size than the distance of the point between the plate from the plate. Okay. So any questions so far?
So will we ever get to questions where you do have a plane that isn't infinitely large, or we're just going to stick to ones that are infinitely large and just use that expression in this course?
Yeah, so we will not be using this exact expression. If the plane of charge, let's say, if this is the plane of charge, then to calculate precisely electric field at certain point, let's say this point, due to that entire, if this is the plane of charge perpendicular, see, like to the screen right now, then the electric field will change with the distance. And you see, when the plane of charge is infinitely large, then electric field, as you see, is always perpendicular to the plane of charge. This is 90 degrees. Every vector is perpendicular to plane of charge. And at every point, this point or this point, at every point, electric field has the same direction, always perpendicular to the plane of charge. So that electric field produced by infinitely large plane of charge is uniform in space. It does not, the magnitude and the direction of electric field does not depend on the distance from infinitely large plane of charge. But if the plane of charge is finite in dimension, then electric field lines would be a little bit not uniform. Here maybe would be like this. That would be direction of electric field perpendicular to the plane of charge, or like this, right? So this angle would be 90 degrees. But at the edges, electric field becomes very non-uniform, like a little bit diverge. But close to the plane, electric field will be perpendicular to the plane of charge. But these edge effects are complicated and we will ignore it. As you will see in the future, like we did in physics 1801, we will deal a lot with like two plates of a capacitor, or for many other applications, we use now two plates, charged plates, but relatively close to each other. Then in that region between the plates, the electric field will be uniform, and this will be the result which we are going to use. But you are right. If the plate is not infinitely large, then at the edges, electric field is very non-uniform. Now changes direction and magnitude. But in this region here, or in this region here, we make assumption that electric field in these regions here is uniform, and electric field is perpendicular to the metal plate and given by this expression. See, so that's how it is in practice. And additional questions or comments?
Sir, I have a question.
Yes.
So are we going to learn about if the planes are not infinitely large, will we learn how to calculate electric field in that case?
No, not in this course. It's possible to calculate this. But you know, if somebody would like to calculate the electric field due to finite plane of charge, let's say if this is the plane of charge with some positive charge on this, and you want to calculate electric field at this point, let's say, then this type of calculation, so electric field at this point would be more or less maybe in this direction. We would have to decompose this into X component and Y component, and you would have to separately calculate X component, that X component and Y component, and calculations are possible. You doing that integration, which we did so far, right? Using, usually you would have to do it now like double or triple integrals using that multivariable calculus. And calculations can be very complicated. And you can calculate electric field. Now, at a different point, electric field would be of different magnitude. An analytical expression, how the electric field depends on the distance and the angle, you know, like what is this angle from the plane, is horribly complicated. So usually this is done by computer simulations or computational physics, because expressions are very complicated. But in practice, it is possible to calculate electric field at any point. If you know distance and angles, it's possible to do, but these integrals are very complicated. So we will be not doing it in this course, because the exercise is mostly mathematics, not physics. So in the previous lectures and today, I am trying to tell you that if you know calculus very well, then you can calculate electric field or electric force at any point in space using that integration technique. But calculations are only simple if you do like infinity long plane of charge or very large plane of charge. But in tutorial notes, I also included a few examples where the line of charge is not infinitely large. Now there are some rings or semi-rings and different type of points. So if you look at the tutorial notes, that's all I will require. What I did in lectures and in tutorials. So focus on these primarily and read the textbook. If you uncover the solutions, okay, when you practice, that is the best way to practice. But I'm talking a lot right now just to assure you that I will not require any complicated calculations on the test or exam, because mathematically, there are mathematical complications which take pages and pages to do. And in some situations, as I'm saying, you have to use computational approach, because analytical expressions are just impossible to derive. So that was my very, very, very long answer to your question. Any additional questions?
Yeah, sorry, Prof. I just had a quick question.
Yes.
When we looked at the example before, just the rod, we know there was other directions, and we know it was dependent on the radius from the rod. Okay?
Could you talk a little bit closer to the microphone, because I barely can hear you.
Yeah, sorry. So when we had the rods in the previous slide. Yes. We know it was dependent on the radius from the actual rod, and we know there was other directions, not just like there was other directions, not just straight up, right? Yes. And then when we did the plane, we say that it's like we can compare it to like a bunch of rods lined up together, correct? Yes. So what happens to those other directions, and why is it not like dependent on the radius when we have like a large plane? Yeah, it's a very good question. Why? So you see, the electric field due to one line of charge is given, you see on this slide, right? That you see the visualization, how that electric field goes always radially away from the rod of charge. And that R is not the radius, that R is the perpendicular distance from that line of charge. It's a distance. So at this point, let's say if I want to calculate electric field at this point, this would be that distance R. Perpendicular distance, it would be 90 degrees. This is that R. Okay, so don't call it the radius. We should call it perpendicular distance from the line of charge. So that is from one. But when you use the plane, and in previous slides, we spent a lot of time in previous slides, and like you said, we divided the plane into many lines of charge. And we did a lot of calculations,
And we derived, finally, after all this calculation, which I don't want to repeat, that the electric force due to infinite number of these parallel lines of planes is independent of the distance. So it's a very strange and counterintuitive. That's why you are puzzled by this, that electric force due to one line of charge depends on the distance, but due to infinitely large number of parallel lines of lines of charge, the force is independent of the distance. You know, so review the mathematics, which I did on previous slides, which is the answer to your question, that mathematics shows you that the final result of the force was independent of the distance from the plane of charge, which is very counterintuitive. I agree with that. But it is true because we did calculations correctly. But this is because you have to find the superposition of that electric force due to infinite number of these parallel lines of planes. And the superposition then gives you superposition, which means that integration gives you this result, which we derived now step by step. So again, it's a very good question. Many of you are, I'm sure, are puzzled by this result, but that is true. That's why I did it step by step in previous slides.
Okay, I understand.
Because in physics 1801, I was always telling you, I remember those of you who took physics 1801 with me, that this is the result, just accept it. We don't have time to derive that expression. So now I am proving to you that infinitely large plane of charge produces electric field given by this expression, which is independent of the distance. And that electric field produced by that infinitely large charge is uniform. You see, electric field is perpendicular to the plane, perpendicular, and uniform in space at every point, no matter how far away from that infinitely large plane of charge, electric field is the same magnitude. So we did these calculations on purpose. I wanted to convince you that no, that is true. So yeah, what I wanted to do on the next slide is I wanted to calculate now the electric field due to a ring of charge. So imagine, so I still have a couple of minutes, so I'm not even sure if I should start. Probably not. But in the next lecture, we will calculate electric field due to a ring of charge. And then we will calculate electric field produced by a disk of charge, So this calculation will be relatively complicated as well for the disk in particular, but that will be done on Wednesday, I should say on Friday, and you will see that in tutorial notes, which I hope you will review before Friday. In tutorial notes, I will be calculating the force exerted by ring of charge on the charge Q0 located at point P. So that will be done also in tutorial notes, and calculations will be very similar to these calculations on this slide where I calculate electric field. So that ring will be important case, because as you know, quite often we have for different situations, loops of wire, circular loops of wire for various applications. So that will be important, little example how to calculate the force or electric field due to ring of charge. So I'm going to do it in tutorial notes and also on Friday in lecture. But because right now the time is essentially finished, because lecture should be about 50 or 55 minutes long. So I will stop recording right now. So I will stop share and stop recording.